You have three pillars of image quality in MRI. You have SNR, spatial resolution, and scan time. SNR stands for signal-to-noise ratio. It's a ratio of signal amplitude, which is predictable and can be adjusted, to the average amplitude of noise, which is random, and it's coming from the patient and the scanner. Spatial resolution is the ability of the imaging system to detect 2 points as separate and distinguishable. And scan time is the time to fill K-space, and is represented by the scan time equation down here, which is equal to the TR, repetition time, times the phase encoding steps, times the number of signal averages. Image quality in MRI is a constant juggling act between these three things. Unfortunately, as you sometimes increase your SNR, your spatial resolution will suffer. As you increase SNR, your scan time will increase. So as a technologist, you're constantly adjusting these parameters depending on your patient to get the best image quality possible. Over here I have two different size voxels that shows you the indirect relationship between SNR and spatial resolution. With a smaller voxel, you're covering a smaller area of the anatomy, meaning you're going to be only imaging a few hydrogen spins per voxel. That decreases the net magnetization within that voxel, which ultimately decreases the SNR coming from that voxel. However, with a smaller voxel, you get better spatial resolution or recorded detail. And then over here on the right, you have a very large voxel that is covering a larger area of tissue, which results in more hydrogen spins and net magnetization coming from that voxel, which increases your signal. But a larger voxel results in less spatial resolution or recorded detail. So this voxel over here on the left tends to be grainy, but is better for recorded detail, sharp edges. And then this voxel over here results in high signal, but the images tend to be blurry. Let's go through the geometric parameters and what happens to the SNR, spatial resolution, and scan time as you adjust them. First geometric parameter is field of view. So I have two different fields of view over here to the right, a 24 centimeter field of view, and then I doubled that with a 48 centimeter field of view. The matrix is the same for both, 2 by 2. As you increase the field of view, you're increasing your coverage of the area, and you're increasing it both in terms of height and width of that box or rectangle that surrounds the matrix. This will increase the pixel size, which will increase the SNR. If you double the field of view, it will result in an increase by a factor of 4 in SNR, which is the greatest influence on SNR that you can possibly have for a geometric parameter. In terms of spatial resolution, as you go from a small field of view to a large field of view, you can see that the pixel size gets bigger, which results in a reduction in spatial resolution. And in terms of scan time, it is not going to affect the overall scan time because field of view is not incorporated into the scan time equation. The same goes for increasing pixel or voxel size. As you increase the pixel and voxel size, you'll have more net magnetization within that pixel, which will result in higher signal. But unfortunately, as you increase the size of that pixel, the spatial resolution will suffer and go down. The scan time will not be affected. With the next geometric parameter, if you keep the field of view constant, and in this case 24 centimeters, but you increase the number of pixels, like you have here on the left, you have a 4 by 4 matrix which equals 16 pixels within this field of view, compared to a 2 by 2 matrix which equals 4 pixels within this field of view. With the 16 pixels, you have smaller pixel dimensions, which equals a higher spatial resolution, but your signal will suffer because you'll only get a certain amount of hydrogen spins or net magnetization within each pixel. The scan time will be affected with the number of pixels because you're increasing the number of phase encoding steps from 2 to 4. Number of phase encoding steps is incorporated into our scan time equation. As for a coarse versus a fine matrix has more rows and columns within this field of view, which results in better spatial resolution because the pixels are smaller, but the signal will be reduced because you have smaller net magnetization within each pixel. A fine matrix will increase the scan time because you're incorporating more phase encoding steps into the equation. So in terms of increasing phase encoding steps, the SNR, spatial resolution, and scan time will mirror those of a fine matrix. As for increasing your frequency encoding steps, that will increase the number of columns you have in your matrix because you're increasing the sampling frequency of your signal. This will result in smaller pixels, which will result in higher spatial resolution, but the signal will be reduced because the net magnetization within each pixel will be reduced. In terms of scan time, the frequency encoding steps are not part of the scan time equation, so it does not affect the scan time. The final geometric parameter is slice thickness, which is the third dimension turning a pixel into a voxel. As you increase the slice thickness, you're going to increase the coverage, meaning you're going to get more hydrogen spins and net magnetization within that voxel, which will increase the SNR. But the spatial resolution will suffer, and in terms of scan time, it will not be affected because slice thickness is not incorporated into the scan time equation.